Looking for a way to travel quickly through space? The universe is full of fascinating locations and objects to discover, from far-off exoplanets to distant galaxies that may contain intelligent life, huge black holes, bright stars, and far-off exoplanets. The problem with space exploration, however, is distance. For instance, Elon Musk wants to permanently settle people on Mars, whereas NASA only wants to deploy astronauts. But even with the most potent rocket in history, a visitor to Mars must face a taxing journey through arid space that lasts at least 5 months. In addition, our nearest star is around 4.5 light-years away, making a visit with existing space technology impossible. If only there was a quicker way to get about in space. The impossible has been done. A recent discovery has enabled faster than light travel. What was discovered and what impact does it have on space travel? Let's find out. Any sufficiently advanced technology, according to Arthur C. Clarke, is indistinguishable from magic. But the majority of us must navigate a world of realities. Fantasy must give place to reality as one matures, and humans come to prefer possibilities over probabilities. In other words, we develop our ability to reason. Today's world is one of the viscerally abstract, where seemingly pointless items can really turn out to be valuable and improbable concepts that can result in significant discoveries. When he was younger, Albert Einstein enjoyed daydreaming about riding a lightning bolt. When he became older and started learning Maxwell's equations, he discovered that the speed of light was intended to be constant, never exceeding or falling below the precise value of 299,792,458 meters per second. With this new information, his idea of riding a lightning bolt was severely complicated. Newton claimed that if he shone a white light traveling at the speed of light, then Maxwell's laws would be broken because the light would be traveling twice as fast. It's obvious that something had to give. There had to be a transgression of one of the two rules. Einstein discovered through some mathematical juggling that Newton's gospel was found wanting. While time and space are relative, the speed of light remains constant. He then started imagining what it would be like to ride an elevator in space and developed an even more speculative notion. As it turns out, gravity does not operate by attraction but rather by distorting space-time. Even though Einstein himself was never a realistic guy, his dreams altered the course of history. Nearly all of today's magical technologies, including the iPhone and GPS navigation, are based on his theory. Einstein's childhood fantasies are to blame for the fact that even the most serious and logical adults have to rush between meetings and read financial reports. Yet this sort of began with the Star Trek television series. In a few Star Trek The Next Generation episodes, Captain Jean-Luc Picard would signal "Warp 1, engage," with a raised hand. Thereafter, stars would resemble dashes as light years passed by impossibly quickly. In Star Trek, the crew uses its warp drive to travel through the galaxy faster than the speed of light. This is due to the fact that the speed of light is still quite slow if you wish to go across the Milky Way. Even the next star nearest to Earth is 4.5 light years away. Traveling more quickly is the answer, but it's not that simple. There is no question that mankind will never be able to fully explore the universe. The Proxima Centauri star, which is the closest one to Earth, is over 4 light years away. For a human to reach there, it would take tens of thousands of years, even with the finest propulsion technology currently in use. Thoughts of building colonies in other star systems are always possible, but no one is likely to make the trip. Is it possible to shorten the distance traveled? There are numerous methods for doing that, ranging from nuclear propulsion to laser-accelerated solar sails. But even with the help of these technologies, traveling during a human lifetime would not be possible. Only those who can travel at the speed of light or faster can actually access the galaxy. Because of this, theoretical physicists have long considered the ideal propulsion system: a bubble in space and time that would allow a spaceship to quickly travel between stars, much like the USS Enterprise did. Our spaceship is safely enclosed in a negative energy balloon by a warp bubble. The bubble's negative energy contracts the area in front of our ship and expands the space at the back. When our starting point is thrown backward, the destination is hurtling towards us. Although the space around us changes, our ship stays still. This is a cutting-edge science study, not necessarily false, but loaded with optimism. Miguel Alcubierre, a Mexican theoretical physicist, published a paper on the subject in 1994 that is largely responsible for the idea's current status among scientists. Alcubierre wasn't only a fervent Star Trek fan at the time. Alcubierre included work on the theory of relativity in his doctoral dissertation at the University of Wales College Cardiff, now Cardiff University. According to the notion, nothing can move more quickly than light. Alcubierre, though, found an apparent opening by using a little imagination. Albert Einstein's theory of relativity has two components according to physicists. The uniform motion of objects travelling at the speed of light is covered by the special theory of relativity, which was developed in 1905. Einstein expanded on these concepts for accelerated bodies 10 years later. The three spatial dimensions we are familiar with, up, down, left, right, and front and back, are inextricably linked to time, according to general relativity. Each mass causes this spacetime to distort. The monumental discovery made by Albert Einstein states that we exist in a four-dimensional spacetime. Time in space is dynamic. It is distorted by large things, just like a tablecloth. Only up to the speed cap established by light can anything accelerate across the tablecloth or through spacetime. On the other hand, the tablecloth itself can distort at any speed, as the cosmos occasionally demonstrates. The original spacetime structure, for instance, is thought to have extended briefly at the time of the Big Bang, and it did so considerably more quickly than any ray of light could. Galaxies that are exceedingly far away from us are still being accelerated by the expansion past the speed of light, making it impossible for their light to reach us. Alcubierre estimated that it would only be a short step to a warp drive based on his discovery. One could reach their destination at a speed faster than light if spacetime were to be compressed in front of a spaceship and expanded behind it to make up for it. The crew would not be aware of the length of interstellar travel because the ship would continue to be enclosed in a bubble. Alcubierre likened it to riding on an airport passenger conveyor belt in a 2017 lecture, saying, "You can imagine that the floor behind you is being created out of nothing, and in front of you it is being destroyed, so you move along." Yet expressing this concept in terms of general relativity immediately raises significant real-world issues. Secondly, you would need to pack a massive mass inside a bubble with a wall thinner than an atomic nucleus in order to distort spacetime so drastically. The bubble would then require two different types of materials to be stable. The area in front of the bubble would close due to the gravity of ordinary mass, propelling the entire structure forward. But the area behind the bubble would also need to grow, much like rising bread dough. Alcubierre asserted that you would require some kind of negative energy emanating an anti-gravity to cause that expansion. The thought experiment was over for the majority of physicists at that point. It would seem that energy, which is equivalent to unrestrained mass according to Einstein's equation, E equals mc squared, must by definition be positive. Yet the quantum theory suggests that it might actually have a negative value. However, it seems to happen on a very small scale and only in exceptional uncommon circumstances. For instance, the so-called Casimir effect involves amounts that are so minute that any technological use appears ludicrous. The inability of scientists to scale up quantum devices to generate the enormous amounts of negative energy required to build a warp bubble is a second issue. That sort of travel appears to be several light years off. At least it was, until researchers supported by DARPA unintentionally discovered the first warp bubble. The Limitless Space Institute LS team, led by Dr. Harold G. Sonny White, a former NASA warp drive expert, made the discovery. Not warp drives or Miguel Alcubierre's theories from 1994 were being studied at the time of discovery. Instead, it occurred during an experiment investigating the energy-producing potential of Casimir holes. The discovery that this completely unrelated research had resulted in a warp bubble required an engineer undertaking the research at the very correct time, one who was familiar with warp technology research and knew what he was looking at. The impact that was really observed had nothing in common with a warp bubble. It was a little modest structure that exactly matched Alcubierre's findings. That was a true warp bubble in the material world, the world's first ever real warp bubble. As a result, warp field theory has evolved from fantastic science fiction to something that we can actually build in the real world using the tools and technology we already have. For the first time, we now know what physical tools it will take to create a real warp bubble. That's fantastic too. Although most people are familiar with warp drives from watching Star Trek, our spacecraft are currently constrained by the constraints of ordinary Einsteinian physics. You must launch something in the opposite direction from the one you want to travel in order to accelerate your ship. This has generally meant burning fuel and shooting out the back of a ship in a forceful physical reaction throughout the history of aviation and aeronautics. This method has the drawback of ultimately running out of things to throw away. The second restriction is that your ship is still constrained by Einstein's equation for special relativity, which states that as you approach the speed of light, more and more of the energy you expend goes towards increasing your own mass. At some point, no matter how much energy you expend, you are unable to go any faster and you never quite reach the speed of light. Things are interesting because of the Alcubierre warp bubble theory. Einstein's equation can be gotten around if you create a warp bubble around the local Euclidean space your spacecraft is in, and then push the warp bubble rather than the actual ship. That still holds true inside the warp bubble, but the bubble itself has the potential to travel faster than the speed of light without violating any physical rules. A micro-nanoscale structure has been found that predicts a negative energy density distribution that closely resembles the specifications for the Alcubierre metric. This structure was found while conducting analysis for a DARPA-funded project to evaluate the possible structure of the energy density present in a Casimir cavity as predicted by the dynamic vacuum model. This therefore makes it possible to look into potential applications for warp fields and potential future research into them. The possibility of a warp drive is now open for formal scientific investigation. Yet the warp bubble shown is very little. As a result of negative energy research utilizing Casimir cavities, which makes use of some of the peculiar quantum physics effects produced by these odd structures, we are talking about nanoscale phenomena. Even if this is just the beginning, it creates the possibility for further investigation into a specific issue of warp bubbles and Alcubierre's equations. Alcubierre was proven to be correct, as it turned out. Thanks for watching another episode of Voyager. While you're still here, make sure to click the video on your screen for more mind-blowing videos about space.